Okay, good afternoon, dear students. In last class, we discussed about the transport number method by Hitchcock's method, the determination of transport number by Hitchcock's method. Okay, in today's class, I am going to discuss about the Hitchcock's rule and how to form the Hitchcock's number and definition of transport number and applications, that is applications of conductometric measurements. First, in yesterday's class we discussed that is a transport number. You are finding the transport number is T positive, that is a cation, and anions. T positive you get here is equals to, you take B and U. V positive divided by V positive plus V negative. This is a transport number of cation when anion P negative, therefore is equals to V negative divided by V positive plus V negative. In this conductance, the definition of transport number or Hitchcock's number. Definition of transport number or Hitchcock's number. Hitchcock's number. Here, during electrolysis, you are passing current is carried by the anions and cations. So the transport number is defined as here. After electrolysis, you are passing the electric current on an electrolyte. Here, it gives the definition of transport number or Hitchcock's number. And the transport number, it is defined as the fraction of the total current. The fraction of the total current carried by the cation ion is termed as a Hitchcock's number, or it is defined. It is called as a Hitchcock's number. You have write the definition of transport number. Here, the fraction of the total current carried the fraction of the total current carried, the total current carried by the cations and anions is termed as Hitchcock's number. Cations and anions is termed as Hitchcock's number. This is not to here. The fraction of the total current carried by the cations and anions is called as the Hitchcock's number. If the positive and negative or the speed of the migration of cation. Here we get a move towards cathode and anode. Here the cations and anions move to the cathodes and anode, and the speed of the migration of cation and anion. Here this formula is given as the transport number of cation and transport number of anion is here. I have already written the transport number of cation and transport number of anion. Therefore, this is equals to V positive divided by V positive plus V negative. Therefore, this anion, this is for cation and this is for anion. V negative, their state of the isolation of ions. State of the anion, this is the state of the cation. Here V positive plus V negative. That is the anion. This is the definition for Redox number or transport number. This is a very important for 1 mark question. Define transport number or define the Redox number. Okay, next the Redox rule. How to get the Redox rule? By experimentally here. Redox rule or the Redox theoretical device changing concentration. Redox Redox theoretical device changing concentration. Or you can write the Redox rule or Redox rule. Redox theoretical device changing concentration and or Redox rule. This is a Redox rule. Here in the Redox rule, you know we already in transport number also the electricity. When we are already seen the ions, that ions are move towards the oppositely charged electrodes. Here the ions, the cations and ions move oppositely charged electrodes. Here the ions move oppositely charged electrodes, and here it is considering the solution and provided the anode and cathode. Here you take a solution of the cell and you take a cell and it's containing solution and it is provided with a cathode and anode, and it is cathode and anode, then the imaginary line is vertically added and drawn, then those vertical lines are divided into three compartments. First one is a anodic compartment, second one is a middle compartment, and third one is a cathodic compartment. For studying this theoretical and experimentally Redox rule here, when the ions move oppositely charged electrodes and under the influence of electric current, here under the influence of electric current, under the influence of electric current, Under the influence of electric current and the speed of the cation moving away from the anode. When ions are moved oppositely charged. Here the speed of the cations. Oppositely charged means the speed of the cations moves away from the anode. Away from the anode will be proportional to the fall of the concentration of ions at the anode. Here the fall of the concentration. Concentration is decreases from anode, and here similarly the speed of the ion moving away from the cathode. Cations, 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 anode away from the anode, and anions move away from the cathode. Anions move away from the cathode. Here the cations are moving in anode and anions are moving away from the cathode, and these cations is moving away from the anode. These are proportional to the fall in the concentration of the anode and ions at the anode, and here the similarly ions are move away from the cathode, and this will be proportional to the fall of its concentration around cathode. Here fall in the concentration of ions in anode and fall in the concentration of anions in cathode. And here the heteros has studied, he is a scientist. Here the heteros studied such changes here. These two changes experimentally used the instrument, and here he studied with the experimentally and gave a general rule. That rule is known as the heteros rule. He studied on these two changes. He has studied the experimentally. He gives afterwards. He studied experimentally. Afterwards, he gives a general rule that is known as the heteros rule. That the heteros rule is defined as the loss of the concentration around any electrode. Here the loss of the concentration. Here fall in the concentration. He defined the loss in the concentration of any electrode is proportional to the speed of the ion moving away from it. Here it is a fall, that is the loss in the concentration of the any electrode around any electrode is proportional to the moving from ion. Here moving away from, the ions are moving away from it. This is known as the heteros rule. Okay, right. This is also one most important heteros rule. Okay, right. The definition of rule of this heteros rule: the loss of concentration, the loss of concentration around the loss of concentration around any electrode is proportional to the moving the ion, the proportional to the speed of the ion, proportional to the speed of the ion, moving away from it. Speed of the ion moving away from it. This is a rule of heat. This is known as a heteros rule. This is a heteros. Next, the experimental study of heteros rule or heteros method. Here the experimental study, here I draw diagram here. This is A, that is anode. This is anode, that is positive. And here cathode, here negative charge. And here two lines of two dotted vertical lines. This is a straight line, dotted straight line. Here, this is a anodic compartment. Anodic compartment. This is a central or middle compartment. Central compartment. This is a cathodic compartment. Cathodic compartment. N here. This is a first. Here you get 4 cations. 1, 2, 3, 4. And 4 anions. And here 5 cations. 1, 2, 3, 4, 5. And here 5 anions. 1, 2, 3, 4, 5. And then here 4 cations. And here 4 and this is a first phase. And next here 4 cations, 2, 3, 4. And 2 anions of comes here from the cathodic to the anode. Here extra 2 anions. These are the 2 anions. Here same 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And here 2 cations comes here only, sorry, 2 anions comes in this cathode anodic compartment only presence here 2 and here this cations and this is a phase. This is phase and then draw a solid line, solid straight line. Next, here the two cations are goes to in this cathodic compartment. Here only two cations and here 6 anions 2, 3, 4, 5, 6. Here pair is 2, 1, only 2, one is positive, negative, only 2 pairs are present. When 2 answer comes here, there are 2 pairs are present here. And here C is present in a middle compartment or central compartment. 1, 2, 3, 4. And here C, the positive 2 and answer goes to here. Here already 4 cations and 2 are added here. 6 cations is present. 1, 2, 3, 4, 5, 6. Here only here 2 anions are present. These 3 are the 4 cations are present and only 2 pairs is present here. This is a third phase and draw solid line. Solid straight line. Solid straight line. Next, here 2 positive and here 1, 2, 3, 4, 5, 6. And here 1 anion is goes to that side. Only transfer of only 1 anion here. Remaining only 5 anions. 1, 2, 3, 4, 5. And these 3 are separated. These 2 are the pairs here. And here same 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And here 1 cation comes to here and pairing is just positive. Only 3 is separated. 1, 2, 3, 4, 5, 6. And then 1 cation is comes to here. This is separated and these 3 pairs are present here. This is the phase 4. You have a solid line or like continuation process. This is a diagram of finding the transport number or it is a Heteros number according to the experimental procedure for finding the Heteros rule, that is a Heteros number and or it is also called as a Heteros number. Here this is a cell, you are considering cell and this cell is containing solution and provided with the anode. This is anode and this is a cathode. Here is provided with the anode and cathode. See denoted as anode is A and cathode is denoted as C. And here let the solution lying between the electrodes. Here these are the solutions containing anions and cations. The solution lying between this electrodes, that is A and C here. This is A and C here. Transferring from this to this and this to this here, and into three image here A and C. This anodic compartment and this anode and this cathode are divided the three imaginary, that is here this one and this one to imaginary. These are divided to imaginary lines, this one and this one. That is a two imaginary lines compartments, that is a anodic. These are divided three parts here. One is the anodic compartment. These two lines are divides these compartment. One is the anodic compartment. Another is the central compartment. The central compartment is also known as the middle compartment, and this is a cathodic compartment. These three are the divided, this A and C. That is anode and cathode, and with the help of porous partitions I and C. A and C and by a vertical lines. Or you can write the A and A dash, B and A dash, B dash. Now you take A and C here. This is a capital A, this is capital C anode and cathode, and here you are taking this one imaginary line, that is A and C here, and the vertical, these are the vertical dotted lines. Then before electrolysis, you not passes current. This is before electrolysis. There are there are 13 pairs of the ions here. Before electrolysis, there are 13 pairs of the ions here. See here, 13 pairs of the ions here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here before electrolysis, there are 13 pairs of ions and 4 being present in each the here. The 4 pairs are present in anodic compartment and 4 pairs are present in cathodic compartment and 5 pairs are present in a middle compartment. Here these 5 ion pairs are present in middle compartment or a central compartment. Here in this, there are in this studying the experimental method. In this, there are 3 cases are arises here for studying this cell for introduction. There it arises 3 cases. It is attackable. It is considered. These 3 cases are considered when the electrodes are not attacked and when they are attacked. When electrode that is attackable or not, the silver or copper, you are in silver or copper, and here it is a attackable or not attackable. You are studying it according to this Petrov rule. Here it comes 3 cases in this rule. Okay, here this figure is known as the migration velocity of ions. The migration velocity of ions. the migration velocity of ions and change in concentration, velocity of ions and change in concentration when the electrodes are not attacked. When the electrodes are not attacked. When the electrodes are not attacked. Here, this is the migration velocity of ions. Migration means it is moving the ions. The migration velocity of ions and change in concentration when the electrodes are not attacked. Here in this, there are three cases when the electrodes are not attacked. When the electrodes are not attacked. When the electrodes are not attacked. The electrodes are not attacked. First one only an answer in case first. Case first is the first case, only ions negative move. Only ions move. Case first is only anions are move. Second case is both anions are cations. And third case is the cations here. When cations are moved double, two times it moves the two times. This is the third case. Here the first case only anions are moves here. When anions are moved, this one moving anions. See here in before electrolysis, here the current is not passed through this cell. Before electrolysis, here there are 4 pair of ions, here there are 5 pair of ions, and here 4 pair of ions. When like 2 ions, 2 anions here, from this 2 anions, from this compartment, cathodic compartment, 2 anions leave cathodic compartment here. The two anions leave cathodic compartment and center anodic compartment. Sorry, here in cathodic compartment, two anions move or enter into the anodic compartment to get the position to here. Here, the first in case first, when two anions in the cathodic compartment, there are two anions are move in the anodic compartment, and it get the position is 2. This is a second position. And although the cations have not moved here only move anions, here not move, and only move only anions, not move the cations. It gets a second position, and it is still we see the number of ions is liberated here. The number of ions is liberated is same. The concentration is not both the electrodes, but we see the concentration in anodic here. This is a these two ions are moved from here, from this to this. Two ions are moved in the anodic chamber has not altered, and while that in cathodic chamber has followed by two molecules here. This is two molecules here follow the concentration in cathodic, and here is a not altered. This get a second position, and if cations are capable of movement of two of the, then enter cathodic compartment. Here the two of the cations, here from this two of the cations, 6 anions are present, 2 Here 4 cations are present, and then the cations are capable of fall in concentration of 2 molecules, and here fall in concentration of 2 molecules in the anodic chamber. Here 2 molecules of fall in concentration, and then in the anodic chamber, and then the fall of concentration chamber is proportional to the speed of ion leaving the chamber. Here the fall in the concentration of the chamber, this chamber, that is the anodic compartment, is proportional to the speed of the living, that is a living chamber, the speed of the living chamber. This is a first case. In first case, only moving the anions, and here the anions are moved in the anodic compartment, it get a second position, and this anodic compartment you have a capacity to move the 2 cations in the cathodic compartment from the anodic compartment, and here 2 anions moves to the cathodic compartment. Here fall in concentration, here 2 molecules, and here fall in concentration of 2 cationic molecules. This is a second position. Then case 2. Case 2. This is a case first. Case 2, when both cations, positive and anion negative move both when both cations and cations and anions move at the same rate. Move at the same rate. We are moving at same rate. Or when cations positive and anions negative move at the same rate. Same rate here, speed. Same speed. In case 2, here you assume that here in case 2, here you in case 1 you completed phase 2. In case 2, the 2 cations move from anodic compartment. See here, this is a 2 cations. Here 2 cations are present. Here the 2 cations are moved from this anodic compartment to the cathodic compartment. Here 2 cations are moving from anodic to the cathodic compartment. Here 2 anions are here. 2 cations are present here, and extra 2 molecules are comes. And here same, that is only here 2 pairs are present, and here 2 pairs are present, and 2 anions move from the cathodic compartment to the anodic compartment. See here. And then we get the position is third here. You get a third position. 2 anions are moved, from anodic compartment to the cathodic compartment, and 2 anions move from the cathodic compartment to the anodic compartment. You have the capacity here also. The capacity how to move the 2 cations, and here also capacity to have the move 2 cations. And then you get a position third. This is a position first is no electrolysis. After electrolysis, you get the position 2, and after continuation electrolysis, here you get a third position. And in this case, there is a fall in concentration of 2 molecules here. Fall in concentration of 2 molecules in each compartment. Here are 2 molecules, and here also, that is 2 molecules, but find the number of ions liberated as both the electrodes is same here. The number of ions is liberated is same here. The extra here, this is the 6 electrons, and here, sorry, here 6 ions are present, molecules are present, here 6 molecules are present, here 2 pairs, and here 2 pairs. Here this is a in same, in this third position is a same concentration. Pauling concentration is same here. And in case third, when cations move at double the speed of the anions. Case 3, when cations move the when cations positive move at double the speed of the anions. Move at double the speed of the anion. The speed of the anions. Okay, here this is a third case when the cations are moving at double the speed of the anions. Here it is double. Cations moving double this rate of the anions is greater than this anions. Moving rate is greater as compared to the anions in the fourth position. Up to third position is completed. Here the only one molecules are moved here in the fourth position. In as in here the two cations from anodic compartment. Here the two cations, this one, and here the two cations from anodic compartment leave and enter the cathodic compartment. Here two cations are leave and here enter into the cathodic compartment, and the speed of the anions is half of the speed of cations. Here the speed of the anion is half. Here the speed of the, already you know, heading is when cation is at double speed of the anions. Here the anion speed is half of this cations. Here the moving speed of the ions, that is half of the cations. Anion speed is half of the cations, and only by one anion enter. Here half of the speed means here the speed is half, double to the anions. The speed is only half, that because of here moving only one anion to in anodic compartment, only one anion is move or leave to the cathodic are present or enter in this, leave only one anionic or one molecule and enter into the cathodic compartment, and the position is 4. This is indicated as position 4, and we observe here the fall of the concentration in anodic and cathodic compartment. Here the fall of the concentration of this anodic compartment, and here the fall of the concentration of this cathodic compartments are 2 and 1 moles. Here this is a 2 and 1 moles because of half of this one 2, and here the speed is considered 2 and the ions is 1. Here 2 and 1 moles, and the number of ions is discharged is again in the same way, and here the discharge ion is continuation. This is here, and 2 and 1 on each electrode, and from these observations you get a formula. This heteros through fall in concentration around any electrode. Here The falling, already I told the definition of heteroabsolute, that is the falling concentration around any electrode is proportional to the speed of the moving I am moving the away from it. This means the falling concentration around cathode here. The falling concentration around cathode is proportional. Here this is cathode and this cathode is proportional to the speed of the anion. Here this cathode is proportional to the speed of falling concentration of cathode is proportional to the moving the ion cations and falling concentration around. So here the cathodic is proportional to the anion and here the falling concentration around cathode is proportional to the anion. This cathode is proportional to the anion. This anode is proportional to the anion. And here the proportionality is cathodic is anions and anodic is cations. This is a formula of Hitchcock's rule. Here I write the formula of Hitchcock's rule for falling concentration around anode. Formula for falling concentration around anode divided by falling concentration around cathode. This is here. Falling concentration around anode is proportional to the speed of the cation. And here this is proportional is equal to the, that is speed of the cation divided by speed of the anion. Speed of the cation, speed of the cation divided by speed of the anion. Speed of the anion. This is a formula of Hitchcock's rule. Falling concentration around the anode divided by falling concentration around cathode is equal to speed of the cation divided by speed of the anion. You write here that speed of the ion. The speed of the anion is written as negative and speed of the cation is written as positive. Here you write that is the speed of and the falling concentration, that is the V positive divided by V negative. You write here the falling concentration around anode, falling concentration around anode divided by falling concentration around cathode. Therefore, this is equal to speed of the cation is V positive and speed of the anion is V negative. This is a formula of Hitchcock's rule. This is a experimental method. Okay, I will stop here in the class. I will continue in next class. Thank you.